Hello everyone, welcome to lecture 16. Today we'll talk about stability of dynamical systems, and in particular we'll discuss the Routh-Hurwitz Criterion. Let's spend a few minutes to discuss the notion of stability. What is a stable system? A stable system is a system in which applying small inputs would result in responses or outputs that do not diverge. There are different definitions for stability, but the one that we're interested in this course is the notion of bounded input, bounded output stability. And this is what it says. A system is bounded input, bounded output stable if providing bounded input to it would result in output which is also bounded. Consider this diagram on this slide. You have a system with an input of R of t and output of y of t. Mathematically, we can show it like this. If R of t is bounded, that means the absolute value of R of t is less than or equal to some value. Let's call it small letter k. For a system which is bounded input, bounded output stable, if magnitude of R of t is less than k, then magnitude of y of t, the output, would be less than or equal to some other threshold. Let's show it as capital letter K. And you can see this in these diagrams. Regardless of how much R of t varies, for as long as its magnitude is less than some number k, you can see that y of t is also bounded. It doesn't go beyond that new threshold of capital letter K. This is a system which is bounded input, bounded output stable. Now let's consider a couple of examples. Think of a system that has one single resistor in it. Now we know from Ohm's law that voltage across the resistor V of t equals R, the resistance, times I of t, the current through it. So I of t would be V of t divided by R. Now if I apply voltage to this resistor, and if that voltage is bounded, that means the magnitude of V of t, the absolute value of V of t, would be less than K. In this case, the magnitude or absolute value of I of t would be less than K divided by R, which is a bounded value. So the system is bounded input, bounded output stable. Let's consider a different example, an inductor. Imagine you have a single inductor which is connected to a voltage source. We know that the voltage across the inductor would be L, derivative of the current. So I of t can be written as 1 over L integral of V of t times d of t. Now suppose we apply an input voltage to the system which is bounded. For example, V of t is the unit step function with a magnitude of k. If V of t is k times u of t, obviously its magnitude is going to be bounded and it's going to be less than or equal to k. In this particular case, it will be equal to k. But for all purposes, we can assume that it's just a bounded input. Now, if V of t is ku of t, I of t would be 1 over L integral of k times u of t times dt. And we do remember that the answer to this integral is going to be the ramp function. So I of t would be k divided by L times t. What does this tell me? Despite the fact that I have provided a bounded input to the system, as time passes, the current magnitude is going to rise. So the magnitude of the current, the magnitude of the output is not going to be bounded, and it's going to go to infinity. As a result, this system is not bounded input, bounded output stable. Now let's relate what we just learned to linear time invariant systems. Suppose I have an LTI system which has a transfer function g of s. I show g of s as a numerator n of s divided by a denominator d of s. This function is known to be proper if it has more poles than zeros. What does that mean? Poles are the roots of d of s and zeros are the roots of n of s. So if the order of d of s is larger than the order of n of s, I would have more poles than zeros, so this function would be proper. Now this is an important fact that we're going to be using it throughout the rest of this course. An LTI system with a transfer function g of s is bounded input, bounded output stable if and only if g of s is proper, meaning it has more poles than zeros, and all the poles have negative real parts. Consider these examples. Here I'm showing you three hypothetical systems with 3 poles each. Let's start with the one on the left. You have 3 poles, one of them is real and negative. The other 2 are complex conjugate poles with a positive real part. Based on what we just learned, this system is not going to be bounded input, bounded output stable. How about the one in the middle? I still have 2 complex poles with 0 real parts, meaning that they are pure imaginary. Again, this system is going to be oscillatory and is not going to be stable. However, the one on the right, we remember that from before that this is a system which is stable. How can I relate to what I just learned? Well, I have 3 poles. All of them are either real and negative, or they have a real part which is negative. So this system is the only system among these 3 which would be bounded input, bounded output stable. Now we're ready to start working on Routh-Hurwitz Criterion. Before we do that though, let's spend a few moments to kind of understand why this criterion is so helpful and so important. Suppose I have a system has a transfer function g of s, which I show it as n of s divided by d of s. If I want to decide whether or not this system is stable, all I need to do is to find its poles, the poles of the transfer function. And I know that these would be the roots of d of s. Now, if this is a first order system or a second order system, this would be simple. All I can do is to find the poles and decide whether they have a negative real part. However, for higher order systems, third, fourth order, fifth order and above, this is not easy without a computer. I'm not going to be able to find the roots by hand. So one way to solve this issue is to use the Routh-Hurwitz criterion. This criterion will tell me how many unstable poles I have in a system without me having to find the roots of d of s. In order to do that, we would consider the denominator of the transfer function, d of s. Now imagine this is an nth order system, so d of s would be a polynomial of order n. The first thing we do is we check all the coefficients to make sure all of them are of the same sign. All of them are positive or all of them are negative. If d of s has at least one coefficient that has a different sign, for example, all of them are positive except for one which is negative, it will at least have one root which does not have a negative real part. And we know that that's a root which causes instability. What if all the coefficients are of the same sign? For example, all of them are positive. Can I conclude that this system is stable? Well, not necessarily. You may still have some poles that have non-negative real parts. So we have to continue with our analysis. In the next step, we form the Routh array. This is a table whose number of rows equals the number of coefficients of d of s. Now the first 2 rows of this Routh array will be filled out based on the coefficients. The first row is going to be A0, A2, A4, and so on, and the second row is going to be A1, A3, A5, and so on. The rest of the rows, however, need to be calculated. Consider the third row, for example. B1 is calculated as A1, A2 minus A0, A3 divided by A1. The next entry, B2, is calculated as A1, A4 minus A0, A5, again divided by A1. And if you wanted to calculate B3, for example, you would continue the same pattern. When you want to calculate the entries in the fourth row, you would use the entries in the second and third rows. C1, for example, would be B1A3 minus A1B2 divided by B1. C2 would be similar to before, B1A5 minus A1B3 divided by B1. You can continue this process until you have filled out the entire table. Once we have the table ready, we examine the first column. The number of sign changes that we see in this column equals the number of poles in the system that have positive real parts. And again, these are the poles that would lead to instability. Let's see this in an example. Consider this system with a denominator of the transfer function S4 plus S3 plus 3S2 plus 2S plus 4. Let's form the Routh table. Obviously, the first two rows will be filled out using the coefficients. The first row would be A0, A2, and A4, which in this case are 1, 3, and 4. The second row would be A1 and A3, which in this case would be 1 and 2. Now let's try to calculate the entries in the third row. B1 would be 1 times 3 minus 1 times 2 divided by 1, which is 1. How about B2? That will be 1 times 4 minus 1 times, well, here I have an empty cell. Empty cell, you can replace it with 0. So I have 1 times 4 minus 1 times 0 divided by 1, which would be 4. This would complete the third row for me. So I would have to go to fourth row. In fourth row, I would use the entries in the second and third rows. So the first entry in the fourth row, let's call it C1. That would be 1 times 2 minus 1 times 4 divided by 1, which is negative 2. And that would be the only entry that I have in this row, because the next column would basically have 2 empty cells, so I'm not going to be able to use it. Finally, I do the fifth row. Let's call that D1. D1 would be negative 2 times 4 minus 1 times 0. Again, notice that I have an empty cell and I replace it with 0. The whole thing divided by negative 2, which would be 4. Now that I have the entire table ready, I would examine the first column. The entries in the first column are 1, 1, 1, negative 2, and 4. All I need to do is to count the number of sign changes. I have 2 sign changes, one from positive 1 to negative 2, and one from negative 2 to positive 4. 2 sign changes indicates that this system has 2 poles with positive real parts. Let's verify that using MATLAB. If I use MATLAB, I can find the roots to d of s, which would be 0.3 plus minus 1.38j, and negative 0.8 plus minus 1.16 times j. Obviously, one of these complex pairs has negative real part and another one has positive real part. So I have 2 complex poles with positive real parts, meaning that 2 poles that could lead to instability. And that is also indicated by examining the first column of the Routh table. Let's do this activity and see if we can actually find out the number of unstable roots in this particular system. The denominator of the transfer function is S4 plus S3 plus 5S2 plus 4S minus 4. What I would like to ask you at this point is to stop the presentation, work on this, and then hit play so we can go through the solution. Well, I should do the first check. I can see that all the coefficients are positive except for 1. This indicates that at least I'm going to have a root with a positive real part, because I have 1, 1, 5, 4, and negative 4. So that's the first test. Using this test, I know that the system is unstable. But just for fun, Let's go ahead and see what else we can find out about the poles. Let's form the Routh table. The first row is going to be A0, A2, A4, which is 1, 5, negative 4. The second row is going to be A1 and A3, which is 1 and 4. Now, I can start calculating the individual entries. So, for example, consider this guy. 1 times 5 minus 1 times 4 divided by 1, which is 1. How about this guy? 1 times negative 4 minus 1 times 0 divided by 1, which is negative 4. I can continue this process and see what the rest of the entries are. I would get 8 for C1 and negative 4 for D1. Now that I have the first column ready, I can count the number of sign changes. I have positive 1, positive 1, positive 1, positive 8, negative 4. So I have one sign change. That indicates that I would have one pole with a positive real part. Well, let's use MATLAB to verify this. I ran this in MATLAB and it shows me 4 roots. Negative 0.12 plus minus 2.35j, negative 1.30, and 0.55. Obviously, the first two are positive, are stable because they have a negative real part or they are a real pole with a negative value. But the last one, 0.55, that's an unstable pole. It's a pole which is real and positive. So that is verified by our test of Routh-Hurwitz Criterion. Now, you might run into situations where one of the entries in the first column actually becomes 0. If that's the case, then you would at least have one pole with a non-negative real part. Non-negative real part means that the real part could be either positive or 0, meaning that it's a purely imaginary pole. Consider this example. You have a system whose denominator is S4 plus 3S3 plus 3S2 plus 3S plus 2. The first row would be 1, 3, and 2. The second row would be 3 and 3. The third row, which is what I want to find for my B1, would be 3 times 3 minus 1 times 3 divided by 3, which is 2. How about my B2? That would be 3 times 2, which is these two guys, minus 1 times 0 divided by 3, which is 2. Now let's do C1. C1 would be 2 times 3 minus 3 times 2 divided by 2, which is 0 divided by 2, which is 0. Now if I use MATLAB to find the roots of the system, those would be plus minus j, negative 2, negative 3. Negative 2 and negative 3 obviously are stable roots because they are real and they are negative. However, plus minus j is a complex pole with a 0 real part. This would be a purely imaginary pole. We can do some fun things with the Routh-Hurwitz criterion. For example, we can use it to find acceptable ranges for some certain system parameters. Suppose I have a system with a transfer function g of s, which has a denominator as I'm showing here. d of s is s3 plus 2s2 plus 2s plus 2 plus k. What I would like to do is to find k in a way that the system is bounded input, bounded output stable. Well, let's form the Routh-Hurwitz table. The first row is going to be 1 and 2, which is this coefficient and this coefficient. The second row is going to be 2, which is this coefficient, and 2 plus k, which is this guy. Now, if I want to find B1, for example, that would be 2 times 2 minus 1 times 2 plus k divided by 2. That would give me 1 minus k over 2. If I want to find C1, that would be 1 minus k over 2 multiplied by 2 plus k minus 2 times 0 divided by 1 minus k over 2, which is 2 plus k. Now, What do I need to have in order for this system to be bounded input, bounded output stable? Again, I would consider the first column. And I would like to have no sign changes. Since the first two entries are already positive, that means the rest of the entries have to be positive as well. Otherwise, I would have one or more sign changes. So that means 1 minus k over 2 has to be positive, which means k over 2 is less than 1 and k is less than 2. And also 2 plus k has to be greater than 0, which shows that k has to be greater than negative 2. If I put these two together, that means k must be between negative 2 and 2 in order for this system to be bounded input, bounded output stable.